Hello, everyone. My name is Marcelo Harris, and I'm the director of the Lewiston Public Library. And I'd like to welcome everyone to the Great Falls Forum. The Forum is a monthly speaker series featuring leaders in the area of business, public policy, academia, and the arts, and is a partnership of Bates College, the Sun Journal, and the Lewiston Public Library. This year marks the 23rd season of the Great Falls Forum, and what a unique season it is. Thank you to those joining us here on Zoom or on Facebook Live. A recording of today's program will be available starting tomorrow on the library's YouTube page. Please visit lplonline.org for more information and the link to that. Please also mark your calendars for our next Great Falls Forum on Thursday, October 15th, with Professor Emmanuel Kayembe of the University of Southern Maine, with a talk entitled Francophonie, Immigration, Cultural Diversity, and Intercultural Identities in the USA. More information about this talk, as well as the Zoom registration, will be available on the library website. So a little bit housekeeping for today's virtual program. There will be time for a question and answer at the end of the program. You can type your questions in, for those of you in Zoom, you can type your questions in the Q&A box that should be at the bottom of your screen, and I will read those aloud. Or if you'd prefer to ask your questions yourself aloud, use the raise hand feature and I will unmute your microphone. For those who are joining us on Facebook Live, go ahead and type your questions in the comments and I will read those for our speaker. And now today, I have the pleasure to introduce Dr. Neil Cummins. Dr. Cummins graduated from Cornell University and then earned his PhD at University College, Cardiff, Wales. He has done research on general relativity, galaxy formation and evolution, identifying and correcting misconceptions about science, and applying what-if questions to interest people in STEM topics, science, technology, engineering, and mathematics. The very first talk he gave on his research was to Stephen Hawking and his group at Cambridge University. Dr. Cummins has been at the University of Maine since 1978, with time at Stanford and NASA Ames Research Center previously. He has published 21 books, 19 magazine articles, over 50 papers, and has logged over 150 radio and television appearances, most recently on the BBC. Please join me in welcoming our featured speaker, Dr. Neil Cummins.
Marcelo, thank you very much for that very kind introduction. I'm honored that you provided our listeners with all of that. Okay, hello everybody. It's a pleasure to be here today. And what I want to do is explore a what-if question. As Marcella mentioned, I want to explore the question, what if the moon didn't exist? And specifically, what if it never did exist? So that's where we're going. And I'm going to do this in a way that's kind of unusual, I think, in this day and age. No PowerPoints. I'm going to use my hands and my voice, and that's it. Okay, so let's begin with asking the question, what if the moon didn't? I should give credit where credit is due, by the way. When my older son was maybe 5 or 6, he had been asking questions like, what's that? Or what that? Meaning he wanted to know the names of things. And then he went through a phase asking why? Those of you who are parents, I'm sure this is all familiar. And then he graduated to asking what if questions. So once, for example, when he fell, he said, well, what if rocks were soft? Then I wouldn't have hurt myself. Things like that. He was very young. But anyways, one day, a colleague of mine, David Batuski, I like giving credit where credit is due. David Batuski walked into my office and he said, we astronomers are thinking about the world too much the same, which is very bad English, I'll be the first to agree, but it was an interesting comment. So I thought of my son's what if questions. And the first question I asked, that came to mind and which I asked was, well, what if the moon didn't exist? And he and I talked about it for 5 or 10 minutes, and then a student came along and he had to go, but I was hooked. And since then, I have been exploring what if in a variety of ways, in written books and the the latest version of the what if that I do is in Minecraft. So it's, it's covered a lot of bases. And so what I am going to do now is explore that first question I asked, because it still always intrigues me. What if the moon didn't exist? And to do that, let's start with the early days of the formation of our solar system, meaning the sun and everything that orbits around it. Now, when the sun first formed and the planets were forming at about the same time, the gas and dust, which condensed to become our planet, was not accompanied by the orbiting moon. So our Earth formed from gas and dust, which pulled together due to gravity, became our planet. Lots of collisions were occurring, and pieces of debris were building our world up. And at the same time, the Earth was being built up. The collisions were not always in the same directions. So if I do a top view here, there were collisions and the Earth started to rotate, spin on its axis. And the young Earth, when it formed, and also, I should say parenthetically, at the same time that these collisions started the spinning, anything that gets smaller and smaller and is spinning, spins faster and faster. If you've ever seen an ice skating performance where and I can't remember there's a name for this particular motion, but at the end, the performer will spin around and then pull his or her hands in like this, and spins faster and faster and faster. Well, the Earth condensing to become the planet, the debris condensing to become the planet Earth, was collapsing also, and had the spinning due to the collisions. And so it spun faster and faster and faster. We don't know how fast it was spinning, but a conservative guess is that when the Earth first became a solid body, the day was something like 6 to 8 hours long. Because as you all know, the spinning of the Earth is what creates day and night. And this young Earth did not have a moon at this time. So we now have the sun and the planets forming, but let's just focus on the Earth. The Earth spinning around very fast due to the condensing and initial rotation. And eventually, our best understanding, and this may be wrong, but this is our best understanding to date, is that a Mars-sized piece of space debris, also in our solar system, collided with the young Earth. And that collision splashed a lot of debris from the incoming body, and the Earth itself splashed that debris, literally splashed it, into orbit around the Earth. So at the time of this impact, the Earth developed a disk. It didn't have the moon yet, but our Earth had a disk of, like if you think of Saturn, for example, Saturn has a ring. Well, there was a ring or disk of debris orbiting the Earth as a result of this impact. We'll get back to that debris in just a second. Just one other quick comment. If this is the Earth's rotation axis, spinning North Pole here, for example, the impact apparently knocked the Earth over, so that instead of orbiting the sun like this, the Earth orbits the sun at an angle, like that. And as a result of the Earth orbiting at an angle, the sun rises in different places throughout. I'll do it from the top view down if you'd like. The sun rises in different places throughout the year. And as a result of the sun rising in different places and staying up in the sky for different lengths of time, we have the seasons. So this impact caused, we believe, the seasons, and also led to that ring or disk of gas and dust orbiting the Earth, which we're going to get to right now. And it is that debris, which was made of rocks and other things, started clumping together. And eventually one clump of this debris orbiting the young, now tilted Earth dominated over all the others. And that debris, here's the Earth, that debris became our moon. We also do not yet know how close to the Earth the young moon was when it first formed. That's still a work in progress. Okay. Now, as time went on, water came to the surface of the Earth, whether it came entirely from impacts of comets, which are mostly water and rock, or ice and rock, or whether the water came from inside, probably a combination of things. But eventually, the oceans formed. And so now we have the moon, which was orbiting, as I say, we do not know how far away it originally was, but we know for absolute certain that it was closer than it is today. And at the same time, the Earth formed oceans. So what? Well, the so what is that, well, I should pause here for just a moment and say there is a common belief, and I've used the expression myself just because it's intuitively obvious, but also wrong. It is a common belief that the moon orbits the Earth, which is to say that the moon goes around like this. And in science classes, we're taught, or students are taught, that the shape of this orbit is an ellipse like this, and the Earth is at one special point in it. And that's wrong. That is wrong. It's not correct. The moon does not orbit the Earth. What really happens, and this was one of the fun things to realize as I was working through this stuff over the years, what really happens is that these two bodies, with the moon about 1/6 the mass of the Earth, 1/81st the mass of the Earth, excuse me, 1/6 the gravity, with the light moon here and the heavier Earth here, the two bodies are actually doing this. And there is a point, it's inside the Earth, about 1,000 miles under the Earth's surface on the way to the center. There is a point inside the Earth where the two bodies are orbiting together, like so. Okay? And there's also a big so what about that, too. It turns out that, well, as you all know, the moon, quote unquote, causes the tides. And that is true, but that's not a complete statement. Yes, the moon causes the tides, but it's not just the gravitational pull of the moon on the Earth pulling. I mean, if you check in science books, in astronomy textbooks, except for mine, of course, you'll often get this wrong explanation that the moon here has a gravitational force that pulls on the Earth, which is correct, of course, and that the force of gravity from the moon is strongest here. It gets weaker as you go farther away from the moon, which is also correct. Okay, and is weakest on the other side. And the claim in many textbooks is that it is the difference in the force of gravity from the moon on the Earth, which lifts the water on this side and leaves the water on this side behind because it's not being pulled as much by the moon. Okay, and that's why there are two tides on the Earth, and that's not right. So what is right is what I just said, at least I don't have to go over all of it, half of it is okay, which is to say, if this is the moon and this is the Earth, the gravitational pull of the moon on the Earth pulls the water on the half of the Earth facing the moon, pulls this water this way, and the water can flow towards the moon. And so that part of the story I told a moment ago is fine. However, do recall that I said that the Earth and moon are orbiting together around a common place called the barycenter, technically speaking, 1,064 miles under the Earth's surface. The two bodies are orbiting the barycenter. And think for a moment when you were children, how when you were on a merry-go-round, I remember this happened to me actually. I was on a merry-go-round and I was holding on when I was maybe 4. And I was holding on to the edge of the merry-go-round, and this bigger boy pushed the merry-go-round faster and faster and faster until I couldn't hold on anymore. And I fell off, I fell back, okay? And you've probably all had the experience of when something is swirling, you feel yourself being pushed away from the center, if not falling off. And that is relevant to the story of the high tides on the Earth. So back to here, moon and the Earth again. This high tide is caused primarily by the gravitational pull of the moon. The high tide on the other side, remember the two bodies are going like this. I'll just hide the moon for a moment. The high tide on the other side, on the opposite side from the moon, like so, this high tide is caused by the merry-go-round effect, which is to say that because the Earth is orbiting around the barycenter, the Earth, feels an outward force, outward defined as away from the moon, an outward force at all times because of this motion. And the outward force on the Earth from the moon as the two orbit together pushes the water on the side facing away from the moon, pushes the water on the side facing away from the moon outward. And that water is pulled away, creating the high tide on the other side of the Earth. So the Earth has, at any given time, at all times for essentially, 2 high tides, one on the side facing the moon, this one, and the other on the side facing away from the moon. Okay. And then one can say, well, so what about that? And there's a lot of so what's here. Okay, this is a top view down from the North Pole of the Earth, okay? So from the North Pole of the Earth, with the 2 high tides and the moon here, it turns out, as you all know, that the Earth is rotating about once every 24 hours. And because of this rotation of the Earth, the high tides are being pulled around faster than the moon can keep up with them, because the moon takes about 27, roughly, days to go around the barycenter once, okay? But this high tide is rotating once a day. And the Earth, with its gravity holding the water down with the moon trying to pull it up, this high tide over here, let's focus on this one for a moment. This high tide over here is not in a straight line with the Earth moon, which intuitively, from what I was saying before, you know, it would make sense that it is, and that the opposite high tide is directly away from the moon, okay? Well, conceptually that's right, but fundamentally it's wrong. And it's wrong because of the Earth's more rapid rotation than the moon's revolution around the Earth. When one object goes around another, we call it revolution. When it's spinning, we call it rotation. So the rotation of the Earth is so fast compared to the revolution of the moon that the high tide is pulled ahead. This high tide now closest to the moon, this high tide is pulled ahead of the moon as the two bodies orbit the barycenter. And as a result, well, this high tide here is made of water, and the water has mass, and all mass in the cosmos gravitationally attracts all other mass. So If this was if this was the Earth with no high tides and this was the moon, the force of gravity between them would be in a straight line towards each other as they go around. But in this case, this high tide, this water up here, is not in a straight line between the centers of the two bodies. This high tide water here has a gravitational pull on the moon this way, which is to say that as the moon is orbiting, the moon is feeling a pull in the direction it's going, stronger than just the straightforward gravity between the Earth and the moon. You can visualize this if you take, for example, a ball on a string, okay, and hang the ball down, just hang the ball down here, and then spin around. And as you spin, you know what's going to happen. The ball on the string is going to start going outward, and the faster you spin, the farther out the ball on the string will go. Well, this high tide here has a gravitational pull on our moon, and as a result, the high tide, pulling the moon in the direction that the moon would like to go rather than towards the Earth. This high tide here is like the string, and the moon is like the ball. And therefore, as a result of the high tide that the moon creates on the Earth, this high tide here, the gravity from this water is pulling the moon ahead of itself, giving the moon extra energy, and therefore causing the moon to spiral away, just like the ball on the string did, as I described turning around. I had a bad hair day, so I won't turn around. Anyways, the consequence of this effect, and also I should say that the water high tide on the other side also pulls on the moon, not in a straight line, but gravity gets weaker as you get farther away. So this high tide here, closer to the moon, is stronger than this high tide on the opposite side of the Earth from the moon. As a result, this high tide here is giving the moon energy, and the moon is spiraling away from the Earth, and has been ever since the oceans formed, and actually before then for technical reasons, because the Earth itself was made oval by the shape of the moon, by the gravitational pull of the moon and the spinning of the Earth. And so that also affected the moon. But let's stay with the water, because that's the real heart and soul of this story. So the moon is spiraling away. And you will sometimes, when you hear presenters say this, and I've done it in a dozen different television shows, sometimes when you hear people say this, what they'll say is the water gives the moon energy, and this energy is causing the moon to spiral away, and it's going around faster and faster, and that's wrong. That is not correct. The water is giving the moon energy, causing the moon to spiral away, but more slowly all the time, which isn't intuitive, but if one looks at the equations and works it out, it works out just fine. The moon is spiraling away, and therefore, taking it back in time, when the Earth-Moon system was younger, the two bodies were closer. And at that time, the moon's orbit wasn't what we would call a month, but much shorter than that. We don't know exactly how short, because we don't know exactly how close the two bodies were when they first formed. But that the geologists are working on that. So the moon is spiraling away from the Earth. But there's a basic concept in science, which is, well, I'll put it in everyday terms. You can't get something for nothing. And since the moon is getting energy from the Earth and therefore spiraling away, albeit more slowly all the time, that energy that is given to the moon from the gravity of the Earth has to come from the Earth. the energy has to come from the Earth. So the Earth has to lose energy at the same time the moon is gaining energy. And the Earth loses energy by slowing its rotation. So the 24-hour day that we have today is very much slower than the, as I said earlier, 6 or 8 hour day, we don't know for sure, when the Earth was young. But the high tide here, and well, in this case, both of the high tides acting on the Earth are causing the Earth to slow down. And the way that happens is that as the water is being pulled forward by the Earth's rotation ahead of the moon, the gravity of the moon is trying to pull that water back. So the water is continually trying to slide back to be in a straight line with the moon. It never does that, but it's trying. But what does that mean? It means that the water is sliding over the Earth's surface, over the solid part of the Earth, which is why we have tides. As the high tide moves and the Earth rotates, and then the location of the high tide on Earth changes throughout the day. And there are 2 high tides every day, of course, because there's one from this side, if you will. And then when we here are on the other side of the Earth, we feel the high tide over here. So that's why there are 2 high tides every day. And as a result of this water sliding over the Earth to try to get lined up with the moon, which it never does, there is friction between the water on the Earth, the oceans, and the land. So the water is traveling this way, the Earth is spinning in the other direction, and then those nasty continents get in the way. And as the water is pushing against the continents, that is what's slowing the Earth's rotation down. So the Earth is getting slower, rotating more slowly all the time. And excuse me, I just want to close something there. The Earth is rotating more slowly all the time, and the moon is spiraling away, which can lead to the question, well, does that mean, I'm sorry, let me just add one thing. Sometimes you'll hear the people who present this on television say that the moon is spiraling away, which is fine, faster and faster all the time because of the ball and the string kind of thing. That's not correct. The moon is spiraling away more slowly all the time. Okay, having said that, the question then is, well, is the moon someday going to leave the Earth completely and fly into space because it's spiraling away? And the answer to that is no, it's not going to happen. And the reason that's not going to happen is if this is the high tide and this is the moon still, okay? As the moon is spiraling away, I'll just move it outward here, the Earth's rotation rate is slowing down. By the way, that's about 1,000th of a second per century. And that is measured, has been measured, about 1,000th of a second per century nowadays. And the moon is spiraling away from the Earth. It turns out, if one does the math, that eventually the Earth's rotation rate slowing down and the moon's orbital rate, the length of a month, if you will, which is getting longer all the time, eventually those two, the rotation and the orbital rate of the moon, are going to be exactly the same. The gravity from the moon will have taken away so much rotation energy from the Earth that the Earth will be spinning, rotating, at the same rate that the moon is revolving. And that will then mean that the high tide will eventually be in a straight line between the centers of the two bodies. If memory serves, that's going to take place, and don't quote me on this, about 15 billion with a B years from now. But the sun is going to blow up, die. It's not going to be a boom explosion, but it's going to die about 7 or 8 billion years from now. So the fact that the moon is spiraling away, you don't have to worry about property investments on that one. Okay, so today, I'm sorry, there's a question one can certainly ask, well, how do we know this is really true? Well, the answer is that the Apollo astronauts, since this question was being very seriously studied in the 60s, Apollo astronauts took a device on the moon, which is essentially a mirror. I'll describe it more in detail in a second, and put on the moon this mirror type device facing the Earth. And scientists on the Earth then fired laser beams from the Earth to the moon to bounce off of this mirror. They still do that today. And what they do is they send out the laser beam, a pulse of light. It bounces off this mirror type device and comes back, and they time the round trip. How long does it take to go from here to there and back again, from the Earth to the moon and back? And the answer is, it takes more time every day, literally. And if memory serves, it's about 2.5 inches a year. So, excuse me, we have the moon spiraling away with experimental proof that that is the case. Let me just say a few words about, excuse me, a few words about the that mirror type device. It's not a flat mirror. It doesn't happen very often. It's not a flat mirror. Think about your car for a second. On your car, there are the red plastic and orange plastic reflectors. And so if you're heading, say, this way, and someone is coming this way at night, the light from this car will reflect off of those reflectors and come back towards you. So, or towards the car that's coming towards you. So the light comes down, it reflects off of these reflectors and comes back. And what happens is that they've designed those reflectors, and you're welcome, I invite you to take a look at them in such a way that no matter what direction the light from another object is pointing towards your car, the light that hits their corner reflectors always goes back in the same direction from which it came, which is why you can see the glowing red or orange reflectors, even if the car that is reflecting them has its lights turned off or it's not going in the same direction. And these things are called corner reflectors because it turns out that if you imagine the corner of a room, there's 3 walls or 2 walls and a ceiling meeting in the same place. If you have a light beam strike any one of those 3 surfaces, the 2 walls and the ceiling, it will then reflect off of that, hit another one of those 3 surfaces, reflect off that, hit the third of the 3 surfaces, and come straight back from whence it came. And therefore, those are called corner reflectors. So corner reflectors were put on the moon. And the neat thing, as I said before, is you don't have to be looking straight on. That corner reflector can be at any angle, and the light will always come back from where it came. And that is what astronomers and other scientists do. They, for example, will take a laser beam and put the laser beam through a telescope. Actually, they use a telescope in the opposite sense. Instead of light coming in, they aim a laser beam through the telescope and focus that laser beam to go to the moon. Anywhere on Earth you can do this because the light is always going to hit the corner reflector on the moon and come back to you. And what they do is they send these pulses, as I've described, with high-tech timers to time the round trip from the Earth to the moon. It's about 2 seconds, give or take a little bit. And that has told us that the moon is spiraling away. So we have confirmation that the moon is distancing itself from the Earth. Okay, so now we have a world where, and this talk, let me just remind you, is what if the moon didn't exist? And I've spent all the time talking about the moon being here, and that was not a mistake. It was intended, because what we're going to do in a moment is we're just going to take the moon away. It never existed, and ask what would the Earth be like then. So we have the moon spinning around, the Earth spinning around, and the moon spiraling away, the Earth slowing down. And today, of course, the length of the day is about 24 hours. So finally, then, we can ask, well, what if the moon had never existed? And that's what I want to then now focus on, since we have a mechanism by which the Earth, well, it's slowing down, remember? So therefore, in the past, it was spinning, rotating faster than it is today. And that changes about everything, but many, many things about our world if the Earth was spinning faster than it is today. So I'm going to take, for conversation's sake, an initial rotation rate of the Earth, spinning rate of 8 hours. Okay, again, we don't know for sure, but there is geological evidence that the Earth is slowing down. It's just going back billions of years to try to find out what it was back then. That's the hard part. Anyways, so let's assume that the Earth's rotation rate was once every 8 hours, and ask the question, what would be different on the Earth as a result of that? Okay, the first obvious thing is that if this is now the sun and this is the Earth, the rotation rate of the Earth being much faster would mean that the length of the day would be shorter. So in that case, in this scenario with an 8-hour day, with an 8-hour rotation period, excuse me, the day would be about 8 hours long rather than 24 hours long. So imagine in everyday life, we have 24 hours of which we're up for maybe 16 hours, round number, a day to do the things that we need to get done. But imagine if the day was only 8 hours long. That would mean 4 hours of darkness and 4 hours of light, again, round numbers, every day. And as a result of that, and yeah, we'll get to the other point related to this in a second. So as a result of that, well, yeah, we're not going to get done everything we need to do in a 4 hours of daylight day. So that is difference number one. The length of the day would be 3 times shorter, and therefore the cycle that life has between waking, doing its thing, going to sleep and waking up again would be profoundly different than it is today. And the issue related to that is, remember I said early on that the impact tilted the Earth's rotation axis, which, well, let me just say a few words about that because it's relevant to this part of the story. The Earth's rotation axis being tilted at, oops, I'll do it again this way, but it's harder to visualize. This way is a year. This is the sun now. This is the Earth going around. So this is 1 year from here to there again, okay? The Earth's axis being tilted 23.5 degrees in real life means that throughout the year, the sun rises in different places in the sky, is up for different lengths of time each day compared to other days, and sets in different places in the sky throughout the year. Now, we are all familiar with that here in Maine because, you know, It's getting towards winter and the days are shorter. The sun rises farther south, farther north, farther south than usual. It goes across the sky more quickly and sets more rapidly than during the other seasons. During the summertime, the sun rises farthest north of east, stays up longest, and sets farthest north of west, summertime now, of any time in the year. And if you sort of draw pictures of that, what you'll see is that because the moon rises north of east during the summer, its length of time in the sky is longest of any day of the year. And around December 21st, the sun is rising farthest south of east. It is going across the sky farthest south from us and is up for the shortest time of the year. And as a result of, this is still real life Earth now, as a result of the sun having different paths in the sky and different lengths of time being up, the amount of heat that the sun can deposit on the Earth at different times of different seasons is different. Obviously, when the sun is up least and is farthest south so that the light rays have are spread out most, we get the least amount of heating on the Earth. That's our winter. And likewise, 6 months later, when the sun is highest and up longest, we have summer. But if the moon had never existed, the impact which we believe splashed the moon's debris into orbit and also tilted the Earth, it wouldn't have tilted the Earth. So without the moon, the Earth would be orbiting around like this, orbiting the sun around like this, and there would be 12 hours of day, like 12 hours of darkness everywhere, throughout the year. So that would be a profound difference between what we have now and what we would have if the moon didn't exist. No seasons, punchline. Another major consequence of the rapid rotation now of the Earth is the fact that the winds on the Earth would be profoundly different than they are now. The winds are caused by a combination of heating from the sun, here's the sun, heating from the sun and the rotation of the Earth, and the location of the water and the flow of the ocean currents. All of these things combine to affect it. But the big picture is that the rotation of the Earth has a major effect on the heating and cooling cycle for the Earth. And the heating and cooling causes the gases of the Earth to rise and sink, heating rising when the day is bright and sunny, and settling, this is the air now, settling down towards the evening and at night. Well, if the Earth was spinning faster, that cycle would be profoundly different of heating and cooling of the air and the length of time that the air is heated and cooled each day. And the consequence of that, again, as best as I can determine, is that the winds would, in many places on Earth, be significantly stronger than they are today because of the rapid rotation of the Earth. And therefore, the wind patterns would be different. And where the wind is typically stronger, faster, it is likely that the biological environment where the winds are stronger would be different than it is today. So let me just pick a number. Suppose there were 30-mile-an-hour winds throughout most of the year at a given place. It is unlikely in those environments that the trees would grow up so high because the winds would be knocking them over. And one can work out a lot of consequences of the effect of the different weather patterns on the Earth if the moon had never existed compared to what we have today. And I think, time being what it is, that I will stop there, and hopefully I motivated you to think about what if and you will probably come up with other things that would be different. Oh, I'll throw out one more just for fun. The life cycle, I said it wrong, the day-night cycle of the humans and other animals is driven by what has evolved in our bodies and is called a biological clock. And the biological clock is synced to daylight predominantly, cycles through 24 hours, and that is this internal biological clock is what helps keep us oriented to, it's daytime, I should be doing this, and it's nighttime, I'm going to sleep. The biological clock in creatures that are on a world with an 8-hour day, fundamentally different. So if you were to go into space, go to some other world far, far away, in the words of Star Trek, and the length of the day on that world was fundamentally different than our 24-hour day, let's say 8 hours, okay? And you decide you want to live on that world. It would be very, very difficult for your body to adapt because your clock's used to 24 hours, it's not used to 8 hours, and things go quickly wrong under those circumstances. We know that today because astronauts in space have to go through a day-night cycle of 24 hours to function well. And the people who live underground have tremendous difficulty on Earth today, have tremendous difficulty functioning well. So there are, as I said, lots of consequences, and I hope that I've shared a few with you to stimulate you to think about what if the moon didn't exist. Thank you.
Thank you very much, Neil. We have some questions that have come in, so I'm going to go ahead and ask those. Gregory asks, if a dark force is accelerating separation of galaxies and star systems, why do you think the ring of material around the Earth coalesced into the moon?
Excellent question. Let me just say that in astronomy, we have looked at the cosmos on large scales, and we, as you all know, live in our Milky Way galaxy with hundreds of billions of stars and other debris. So this hand is now the Milky Way galaxy, and there are other galaxies, billions of them, and we astronomers have looked at the other galaxies and compared their motion to ours. And many of the other galaxies in the cosmos are moving away from us. The universe is getting bigger. And if we calculate the amount of gravity all of the galaxies have pulling on each other and figure out, well, how fast should they be moving apart? And should they be slowing down? Because gravity, as you all know, slows things down. You jump up, you slow down, you come back, okay? It turns out that there is an expansion of the cosmos that it's expanding faster than it should. It's not only expanding faster, but it's accelerating apart. The galaxies are accelerating apart. That is what we call dark energy. There's another dark thing in the cosmos. In a galaxy like our Milky Way, if we look at all the orbits of all the objects in our galaxy alone now, they do not respond to the gravity of the things we can see. There's got to be other stuff there, and that's called dark matter. And so the question is, if dark matter and dark energy are pulling the young solar system away from itself, the gravity of the things out there, the dark matter in our galaxy, the dark energy of the expanding universe, are pulling the matter apart. How was it that the Earth and Moon and Sun, et cetera, could form in the first place? How did that disk of gas and dust around the Earth form the Moon? The answer is, it turns out, that the effect, the strength of dark matter and dark energy on distances of the size of our of our solar system, are so weak, gravity is strong enough to overcome them and form the objects that we have today.
So another question we have here comes from Audrey. Why don't rivers and lakes have high tide and low tide?
It's an excellent question. In fact, if the lake is big enough, it can have a high tide. But the point is that if you have a river or just a regular sized lake like we have here in Maine, and you calculate how much the gravitational pull of the moon can lift that volume of water, which is tiny compared to the volume of an ocean. If you calculate how much the water of a lake can be lifted up, or of a river flowing can be lifted up, except in extremely large bodies of water, the amount of gravity from the moon lifting it up is too small for us to detect compared to the effects, for example, of the wind or other things that happen in everyday life. So the answer is the gravitational pull of the moon is too weak to cause small bodies of water, lakes, rivers, and so on, streams, to rise and sink, so to speak.
Thank you. We do have somebody asking to talk. So Madeline, you have your hand raised. I'm going to give you permission to go ahead and ask your question when you're ready.
Okay. I'm not Madeline, I'm Roger, the husband. And in regard to biological impacts, if we didn't have a moon, currently we're losing our insect population. I'm wondering, I'm assuming that effect would have occurred, but dramatically, if we didn't have a moon. Is that correct?
Well, let me just ask you a quick question related to what you just said. The insect population we're losing today, why?
Loss of habitat, climate change, and there must be other factors as well.
Okay, that clarifies it. Thank you. Then the answer to your question is the difference of the rapidly spinning Earth, spinning 3 times faster, 8-hour day, would be so profound that the life cycles of all creatures and the dynamics of the flow of water, the winds and so on would be so significantly different than we have today that the creatures that evolved there, there's another punchline to this story which I'll just throw out. Those high tides I was describing before, when the moon was 3 times closer, those high tides were 1,000 times higher. And those high tides back in the day were strong enough to cause a lot of debris from the land to be washed into the oceans back in the day. And it was in those environments that life evolved. Well, if the moon had never formed, there wouldn't have been these high tides to put debris into the oceans, and it would have delayed significantly the length of time it takes for life to evolve. So we wouldn't be here today discussing it. However, let's pretend that, say, 5 billion years from now, before the sun explodes, life did evolve on that rapidly spinning Earth with the different biological cycles and with the different wind flows. There would be profoundly different animal and insect life. And it would have to adapt to much more challenging environments than the insects today. So I would say that because the environment would be so much more challenging for insects on the no moon Earth, that they would probably not have as much difficulty adapting as do insects today on a more tranquil world that we live in.
We've got quite a few questions coming in, so in the interest of time, I think I'm going to have to pick and choose a little bit here. So Catherine asks, if we wouldn't have seasons without the moon, what would our weather in North America typically look like?
Oh, that's a good question. I would say that number one, it would be windier. Number two, there would be fewer profound storms like hurricanes, like hurricane that is hitting the south coast of the United States now. There would be less of that, but there would be more continuous blustery days than we have today here in North America. And it is likely, and again, the details are unclear, that the places in North America that are moist, like we have here, or that are particularly dry, such as in the Southwest, would have profoundly different weather systems than we have today. The details are so complicated that I honestly don't know the answer, and it would take a lot to work out the details. Short answer is they would be very different than we have today.
Bruce asks, why do we only see one side of the moon?
Okay, an excellent question. If this is the Earth and this is the moon, when the moon first formed from that debris, that debris, when it condensed to form the moon, there were lots of impacts. And therefore, when the moon first formed, it was literally liquid rock because of the impacts that formed it. And whatever rotation rate, whatever spinning the moon did when it first formed, the Earth acting on the closer moon would have created tides in the rock of the young moon. And those tides in the rock of the young moon, as they slid over the moon, they would literally cause the moon to change its rotation rate, so that one high tide on the moon now, one high tide on the moon was always facing the Earth. And then the moon solidified, and the rotation rate of the moon was fixed. And therefore, ever since then, because of tides of the rock on the moon, the same side of the moon always faces the Earth.
And this question is from Jim, is the melting of the ice caps together with the rise of sea levels affecting the movement of the moon relative to the Earth?
Love it. Yes, the answer is yes. Next. No, what happens is that there's more water out there, liquid water, excuse me. It's more liquid water, and therefore the oceans have higher tides as a result. And all of the things I described earlier apply, but with a greater pull from the Earth on the moon.
I think we may have time for a couple more here. So let's see, we've got one from Peg. We learned that high winds like 200 miles per hour in ancient geological time formed the red rocks of Sedona, Arizona. Was that a result of the Earth's relationship to the moon back then? Or would our surface formations be different because of higher winds? Would those winds have been greater than 30 miles per hour?
Wow, fantastic. Those are primarily geological questions, but the short answer is yes. It is likely that the high winds there in Arizona were, at least in part, due to the more rapid rotation of the Earth, which would have affected the weather, which would have affected the rain, which would have affected essentially everything. And as a result, what the real Earth was doing when it was spinning faster, it was evolving much more differently, if that's the right expression, than it is today. And therefore, consequences like you just described are very likely to have occurred. There are also likely to have been other details, but I don't know if we know what the other details would be. Short answer is yes.
So that actually brings us to 1 o'clock. So I'd like to close questions now. Thank you very much, Dr. Cummins, for joining us today. Any final thoughts or words for us before we go for the day?
Well, we have the opportunity to make the earth a better place. And we could do otherwise, but we have the potential, we humans have the potential of making the world a better place by taking care of it and preventing bad things from happening. And I urge all of us to do those things.
Thank you to everyone for joining us today. As a reminder, we will have a YouTube video up of this presentation tomorrow, so look for that on the library website as well as the library Facebook page and the YouTube page, of course. Thank you again, and have a wonderful day.